Welcome to the lecture. So if you were not attending synchronously, this is a repeat that I'm doing the next day, because during my lecture yesterday, our lecture 7 to 8, so around 7:30, there was a power outage. I'm kind of annoyed that they chose exactly in the middle of my lecture, not before, not after, to do it, but we press on. So in order to make up for that, I decided to just re-record this from scratch rather than upload the 2 halves that I had, where I was kind of rushing because I had lost about 10 minutes in the middle. And so this is just going to be me sharing what I had planned and talking over it. So today we're talking about probabilistic programming, and that is a big and fancy word for something that sounds scary and has a lot of math to it, but not really. Like, you can start making inferences and start reasoning about these things intelligently without the full-blown discussion of the math. This is not a statistics class. I couldn't hope to possibly cover all the stats you need to know in your entire career. I can just hope to give you an insight into how these things are used in the real world and computationally. And I think it's much more useful as a researcher to have an idea of where something is a good tool than to necessarily know every single detail of it, but not to have that other level of insight of, do I even want to use this? So this is a high level discussion. If you're interested, come talk to me or like look around online for the more intense math version of this. So why are we talking about this at all? Tons of science basically just comes down to making models. Like, you have some data X and some other data Y, and you want to build a relationship between them. So we're trying to, in more mathy terms, find a function f such that this relationship is as exactly satisfied as you can hope to get. And these input and output data points could be literally anything. Like, a very simple version would be, I put some voltage across a resistor and I measure the current flowing through it. And that should follow a really easy linear relationship of, I'm going to say my input is the voltage difference and the output's the current, or you could say the other way around as well. And that's really easily predicted by Ohm's law, V equals IR. And you can scale up to like more complicated circuits, for example, where you've got this function isn't necessarily linear, or it's not necessarily just, maybe it's got some time dependence to it as well. Maybe it has some derivatives in there. But essentially, it just comes down to predicting some sort of relationship between two variables. That's the simple case that we're going to consider, and the paradigm that covers a lot of interesting inference. For example, a really slightly more like astro one is, it's relatively easy to measure the radius of a planet and a bit harder to measure the mass, or you can only measure one or the other sometimes, depending on how you detect it. So if I tell you the radius, what's your best guess at the mass, and vice versa? And that's just a really interesting thing to be able to find out. What's the function that translates like R as f of m or m as f of r? How do you find that? So this basic setup is a gateway to a lot of really interesting science. Probabilistic programming is one particular pretty common approach to it, which is to say, set this up as a question of probability over a bunch of different models. Given a certain set of concrete data you've got, x1, y1, x2, y2, and so on like that, what is the f that is the most likely to describe this data? And to make that more concrete, let's say we define a specific set of functions that we could be looking at. So you usually say like f is indexed by p for this notation. If you've got possible models where f sub p, or f sub p of x is mx plus b, just a simple like line that we would have learned about in like high school algebra classes, where this is strip and this is the intercept, then what choice of these parameters p matches the data most precisely, or maximizes the probability of these parameters p given these data xi, yi? How this is usually done is a Bayesian method, which is this is a pretty common theorem, Bayes theorem, which is essentially, it breaks down into evaluating a likelihood, which is to say, okay, if this is the true relationship, if y is 3x plus 2, then what is the probability that these data come from that with some like noise attached to it? What's the likelihood that if I plug in 2, I will get 7, which would match the, sorry, if I plug in 2, I would get 8 for the case 3x plus 2. Like how closely do these data match the hypothesis that a certain p is the correct one? And then there's also a prior, which is, it has a really nice intuitive bit of reasoning to it in science, which is essentially something someone else told you, information that you have from before. Like usually when you're experimenting on something, you have some like prior belief, maybe from theory, maybe from previous experiments or something like that, that a certain value is correct or is incorrect. And so you can add in a mathematical term to reflect that. For example, Hubble's constant is, I believe, about 70 in the units that it's in, like kilometers per second per megaparsec, I think. So if you have a model for something cosmological that says the Hubble constant is 3, that's probably not it. That's probably not correct, and there's an alternative explanation for your data. So you want something in your math to reflect that. And so the prior is a bit more of a design choice. You don't have to worry about the exact math of this, just the idea is we're going to be working with likelihoods and priors, and primarily likelihoods. We'll be building these functions and seeing what they tell us. Okay, so how you might think to approach all of this, and this is a bit more pre-written than I thought because I did some of this yesterday. How you might think to approach this is, well, why do I have to care about the probability side of any of this? And just think about it as a mathematical optimization problem. So let's try and think about that, because that's going to inform how we go about this more intelligently with probability. Let's go back to our linear model and say f sub p of x is mx plus b, where p is just a vector containing this number, the slope, and this number, the intercept. What m and b best describe our data set? If you were given this as a problem in Math 1A or an equivalent Calculus 1 course, you might think to use differentiation. You're told if you want to optimize something, which seems to align with like something being the best. If you want to optimize something, then you take a derivative and you set it to 0. The things I want to vary are these parameters p, so I take a derivative with respect to p. And I'm going to say that the thing I want to minimize or maximize is this quantity L. L is short for loss, and it's a pretty common term in these kinds of things. And so you might think, well, what's a good way to describe the loss? You'd like look at the model, you'd look at where the actual data are, play around with it a bit, and you might land on this, which is to say, for every data point, I'm going to look at how far off my model is. My model is this one, and my true value is this one. And we look at how far off that is and add up all the squares of these things. I want to add up the squares rather than just adding up the values themselves, so that I don't just like cancel out. If I take, for example, this one's off by some positive value, this one's off by some negative value, if I add those up, then I might just get 0. And that's not what I want, because that's actually a pretty bad model compared to something where both of these are just on the line. So you can derive the optimal coefficients really easily. If you take these derivatives, you get 2 equations in the 2 variables m and b, and so you can exactly solve that and you'll get the values. And if you take a physics-based lab class here, the 5BL or 5CL or the 111s, you'll probably do something like this pretty early on. And so that's essentially what you're doing. That's where those values you're working with come from. So far so good. And in terms of coming back to computation, we can even go further and say we can do all of this in linear algebra. So another way of referring to this is least squares solving, because you've got a sum of squares over here, and you're trying to minimize it. You're trying to make it the least value you can. And so you might think back to a linear algebra class where you're told, well, to solve least square systems, I put an A transpose over here, and I solve it like this. And while this inversion step is a little computationally expensive, there's workarounds for that. And so in principle, every time you want to figure out a relationship between some data, you can put it in a matrix like this, and you can verify by like doing this matrix vector product that this is actually mxi plus b is yi. In theory, if I just put everything I want in a matrix, and just solve for this little vector right here, I've got everything I need about that data set. Okay, so why do we need to talk about probability? Why didn't I start by saying this is a lecture on linear regression? Well, linear regression definitely has its place as a sort of sanity check, or even based on some physical situations, your full analysis technique. Like you do a lot of things in those lab classes where it's really all you need. But it's a bit limiting as the only theory we have. Let's take a look at why. There's 4 major reasons I believe linear regression is a bit limiting as our only analysis technique out there. One, it needs you to be able to take a derivative. Our derivation for it, I didn't write out the exact coefficients because it's just cluttering up the screen and I don't really need to, but you could. Our first set of derivatives, we need to be able to take them at all. So you might think back to the Ising model that we did in homework 1, which, if you recall, says I've got a bunch of particles that can either be spin up or spin down. And when they're all spin up together, they create a magnetic effect. And so alignment reduces the energy of the system, and systems want to minimize their energy. But as soon as I add in a thermal component to that, there is some disorder to it. So this sort of push and pull between these two factors. Thermal energy wants to mess everything up and make it like equal amounts of spins up and down. And magnetism wants to align all the spins. So you see how those two factors balance each other out. We actually solved this using a Markov chain Monte Carlo method, which we're going to see what that is in a minute. We were using this without really knowing we were using it. Sort of skipped over those details there. But anyway, the point there is what we were optimizing was energy with respect to a set of spins. With respect to the first particle is spin up or down, the second particle is spin up or down, the third particle is spin up or down, and so on like that. But those values are all plus or minus 1. It's up or down. Calculus fundamentally needs you to be able to alter an input a little bit and get a change in the output. But you can't do that if you've got spin up and down. There's no such thing as altering a spin up state a little bit. There's no such thing as 1.01 spin. Therefore, this quantity here, dE over ds sub I, doesn't really make sense as a thing you can talk about. Then if you try to write this out as a limit, it just wouldn't exist. So we can't do that with linear regression. A naive way to get around this would be try every possible configuration. For like n particles, there is like 2 to the n different setups we could have, which is like I have 2 choices for the first one, 2 choices for the second one, and they're all independent. So I eventually get 2 to the n. So I could write code that would loop through every single one of these and let the first one be -1 or 1, let the second one be -1 or 1, third one be -1 or 1, and so on like that. Compute the energy for that whole configuration, add it to a list of 2 to the n energies, and then find the minimum of that. And that would work. It would be exceedingly slow and take up like way too much time and compute power, and most of your results would be absolutely unnecessary, because ultimately you are getting, say, if it's like, if you have n of 100, which isn't even that high, you would need something like 10 to the power 30 compute steps, and I'm throwing out all but one of them. It seems pretty wasteful, but that would work. And I want to keep that in mind as we develop MCMC, because that is going to be a really useful idea. We've got the idea that we could brute force it. We just need to do it a little more intelligently so that we don't compute things we just want to throw out later. Moving on from that. The second one is the model itself is a bit limiting. Sure, a lot of things are linear, and a lot of things can even be transformed to linear. This is a trick you're probably going to see in lab classes a lot, where 2 variables have like this power law relationship between them. And so you get to take logs, and it's basically down to linear regression on the logs of both the input variables. You could do that, but you can't do that for every model. Not every map that you could apply is 1-to-1. Not every regression is just one independent variable to one dependent variable. And so this is a bit difficult to work with. It's a well understood problem with a lot of techniques out there, but again, we have the sense that we want more. We want to be able to do more. We want more freedom to let our math reflect the reality of our science. The third thing is it's a bit limiting in how we assume errors work. So we assume we want to minimize the sum of squares of deviations between the model and the true data, which is a really, really good starting point and is pretty commonly used even in the more complicated models I'm going to talk about. In fact, it does have roots in statistics, which I'm not going to talk about specifically, but if you're interested, you can look up the Gaussian distribution, the central limit theorem, to see why a sum of squares is actually a really good thing to want to minimize. Essentially, sum of squares is very closely related to a distribution that models just any kind of general noise that we can't really fit into anything else. It's a really powerful result, actually, that all of the different sources of noise pretty much fall into that pattern. But sometimes we have sources of noise where that doesn't exactly apply. It applies in like certain limits, but sometimes we have a more accurate idea of what's going on, and we want our math to be able to reflect that. So for example, let's say I have some input variable, but our output variable is a number of photons hitting a detector. This is a discrete number. It's like, it's an integer. It's 3 or 10 or 300, something like that. I can't have half a photon hitting something. Therefore, it doesn't really make a lot of sense for me to say the model, the model and the true data have a distance of 0.5. That's not something I want to work with because 0.5 is equally as wrong as 1 in this case. Like, are you predicting 36 photons or 37? 36 and a half photons doesn't really work. So the objective here, it turns out, you can make your own model of how this error works. Is a pretty common one. Again, this lecture is really just going to be filled with things you can Google if you're more interested, but no worries if not. This is just to get the high-level sense. It's this complicated thing. And I want to be able to work with that. I want to be able to set up matrix equations that will optimize for this. Finally, sensitivity. Suppose you run this regression and you find that there's some parameter mu that is 0.1, and that describes the data well. That's a good start, but it's not yet a science result. Science results always need error bars. And in particular, I want to know if I alter this a little bit, how is it going to change things? And that can vary wildly. So these are the exact same two lines, the red line and the dotted red line, on this one and this one. And on the left here, you can see that I pretty much just drew this by hand, so maybe even the dotted line is a better description, but the dotted line is probably about equally good at describing this data as the solid one. Whereas here, if I go off this line, the dotted line starts like skewing sort of above all their actual data points, and it's not a really good model. So in both these cases, the solid red line is, let's say, the line of best fit, but that doesn't tell us all we need to know. I want to know something about what happens if I like move away from that a bit. What does that tell me about the science? Ultimately, I'm looking to use this as a science tool, not just as a black box of math and statistics. Okay, so we've got some problems. Let's see what Markov chain Monte Carlo is and how to solve it. Markov chain Monte Carlo is a lot of fancy words. Fortunately, we have seen the Monte Carlo part before. If you recall homework 1, we did this, and again in homework 3, actually. We did the pi approximation analysis, where we picked a bunch of points in a unit square and saw how many of them are inside a unit quarter circle, and count them up, and that's approximately pi over 4. We picked points at random and repeated something many times and averaged them out. It's a really cool, useful technique, and this is why. This is our connection from Monte Carlo techniques in general to specifically applying them to science problems. And the connection comes in the form of the Markov chain part. And a Markov chain is just a probabilistic way of saying, I'm going to make a random guess based on what my last guess was. That's not exactly the definition. It's a more formal thing, but that's what we can work with right now. instead of picking just another random point in the square, I'm going to pick a point that's, say, somewhat close to where I was. And that's maybe not a good approach to the pi approximation analysis, but it's a really good approach when you have a massive space to search for something like the optimal spin strategy, the optimal configuration of spins, and I want to just change one thing at a time and see how it affects it. And that's how you might approach it even just as a person, like playing around with this thing. So the easiest entry point to MCMC techniques in general is what's called the Metropolis-Hastings algorithm. This was actually developed as a physics tool, and then they sort of backfilled the statistics part later when statisticians got to it. Essentially, it's a rule for doing this part of it. It tells you, based on what the last number was, what next number should I go to get to a certain result that I want. There's a whole, there's a way to derive how this is going to give you the exact answer you want and to define exactly what that exact answer you want is and everything. But here's the sense of it. Let's say I'm at a state P in some space. I'm going to propose that I go to a state P prime. So I'm going to pick another thing P prime. So let's put some numbers to this. Let's say I'm at 0.1 and I want to go to 0.11, or I'm going to suggest that I go to 0.11. Now, the next part of this is I want to just figure out, should I go there? So I ask, is P prime better than P? So that'll be some other function. Let's call it except 0.1, 0.11. So I call this other function except that I write for my particular case. Let's do all of these in red for the example, actually. And if except says yes, then you move there and you start again from 0.11. You say 0.11 is a better description of my data, and therefore I'm going to start from that next time. I'm going to forget I was ever at 0.1 other than when I'm saving results. But as far as picking the next state after that goes, I indicate that I am now at 0.11. So 0.11 gets added to the chain. If no, you should sometimes still move there. And there is a very precise way to figure out exactly what that probability of doing that sometimes should be. That's, again, not really important because it's not what you're going to be working with as a scientist. You're not going to be directly tuning these probabilities, but you are going to be working with the overall results of this process. If 0.1 is a good description, you should sometimes still go to 0.11. So here's why. Let's say we've got this over here, and I am, whoops. Yeah, let's say we've got this over here. And I've got 0.1 over here, 0.11 here. And what I'm plotting is the loss function, the same thing we were working with trying to minimize before. There is still a loss function that we are trying to minimize that we're just evaluating at each individual point. In this case, it looks pretty clearly like we should make the move because the loss is reduced over here. So you make that jump, fine. But if you have this whole view of it, then you notice that, well, that's not the absolute minimum. That's probably not the best description of the data. The best description of the data would really be down here. So I want to leave that possibility open. So now let's say my other proposal is move back over here to 0.09. Now, on the face of it, it seems like you would want to reject going to 0.09 because that just makes the loss worse. I can't draw 9s today. Okay, that'll do. Because this jump will make the loss worse. I wouldn't want to ever do that. But you leave open the possibility that just for the sake of exploring everything, maybe there's something better on the other side of it. So I'm going to give it a shot. And if everything in it says, no, move back to where you were, then we can move back to where we were. But I want to be able to explore this part of the space as well. So sometimes I still make this jump. And that's going to enable us to get to what it turns out is the actual solution down here. And we're just going to do this over and over again. We have this sequence of jumps where sometimes you stay still and sometimes you move off. And you keep doing that, and you store exactly where you were at every point in the chain. And then you just end at some point when it looks like you're close enough. And we'll talk about what close enough is. Basically, it's like a way of making educated guesses about what's going on. It will get you the right answer. Like I said, there is a way to prove that. I'd love to talk to you about it if you're interested in it. But more importantly, it solves all 4 problems that we had. There's no sense of derivatives because we're not moving necessarily in a continuous space. We're making a jump. And what that jump is can vary case by case. It solves nonlinearity. You're assuming like very little about the model. The model could be anything for which you can write a loss function. We've just reduced all fitting down to minimization, and we've given you a general minimization technique that will work even if you don't have the tools of calculus. It fixes errors. The fact that you're exploring the space and sometimes going into wrong guesses reflects that there might be like weirdness about your data that maybe isn't captured by like how coarse linear regression is. You can see how important a certain region is just by how much time you spent there. And it also solves sensitivity for about the same reason. Again, if you spend a lot of time somewhere that's not necessarily your like main averaged out solution, you can say, well, sometimes this might also be a good description. And I think it's really useful as a science tool to be able to do that. Even if you have a problem that could be solved by linear regression, if you try running MCMC on it, you could find out something that's not quite linear. There is some sort of skew to all the way the residuals work, something like that. And there's going to be like a lot of qualitative reasoning you have to do as a scientist to figure out why that is. There's a lot of detective work there, a lot of information you're picking up that you wouldn't necessarily pick up if you were just doing linear regression out of the box. So you get to explore regions of this parameter space that you don't necessarily see. So a bit more on what I mean about that is if I had these data X, Y, what I mean by that, sorry, and I fit this line through it, effectively what I'm doing is I'm picking a single, when I'm doing linear regression, I'm picking, let's say this is mx plus b. Let's move to another axis over here. Now this one is m and this one is b. I'm going to call this parameter space, which is a pretty common term you'll hear in MCMC analysis. Effectively, what I'm doing here is by choosing a single m and b, I'm picking a point in parameter space over here. But I have no sense of what the rest of parameter space looks like how far out is this line a good description here? You could imagine I like vary this a little bit, for example. I move this line up a bit. I moved a data point too, but ignore that. And correspondingly, I can move this line up on the b-axis. And now I've got a different point there. But I still only see one point when I do linear regression. And that's a bit limiting. What MCMC is going to get you if you walk around this space a bunch and average out all your results is you'll get the same central point, but you'll get some sense of spread around it as well. You now have a whole region, and that region might peak over here. You might spend most of your time there, but you have some sense of, oh, I could wiggle M this much, and I could wiggle B this much, and you would get the same results. Now, you might be thinking, if you've already seen something like error analysis in lab classes, well, why can't I just do error propagation? There is a whole theory of error propagation, and it's quite good to use. But error propagation assumes everything's linear and perfectly modeled in some sense. And that's a really big assumption to make as a scientist going into something that's like big and unknown. I don't want to be limited by that. I want to be able to look around the space and see what I can see. So even on continuous problems where linear regression works, depending on your data set, the size of things, and just general structure of everything, it might still be useful to try and get this like wider sense of how your parameter space is structured. Like maybe you get something like really weird and non-linear like this. I've gotten some really strange things, and you wouldn't be able to get that from error analysis. Turns out it's really, really good at, this model is really, really good down here. even though it's not good like here or here. If I just vary one of these, it doesn't work, I have to vary both. What's going on with that? What does that tell you about the science of whatever you're studying? These are interesting questions. These are the questions I want to be asking as someone studying whatever science subject this is, a star or a planet or whatever. Okay. There are other MCMC algorithms, but I'm already going to go a little over 50 minutes, apologies. So I'm just going to show you this section instead of telling you about it first. So I'm just going to pause for a moment. All right, and we're back. So on the screen right now, you should see both a demonstration of the algorithm and a terminal. We'll worry about what's on the terminal later. It doesn't even really matter if you don't want to read what's on there. It's more just for our convenience. So over here is a really nice visualization of what the Metropolis Hastings algorithm actually looks like in practice. So you've got this distribution in the like banana shape that this website has, where I want to figure out what the shape of this thing is just by walking around. And you see this arrow over here, which is making and accepting or rejecting these proposals. So it makes a proposal by like where it points its arrow, and then sometimes it'll accept it and sometimes it'll reject it. So notice that most commonly it accepts and flashes green and moves to that point for a proposed state that's within the distribution very visibly. And it most often rejects points that are really far outside it. So you see it proposed this one down here, for example, and rejected it. And that just means like there was some chance you went there, but that probability was so low that it didn't actually come up. But the fact that you do that allows you to capture not just the peak of the distribution, but the tails as well. This point down here is probably a probability and was almost certainly moved to from a higher probability state. But if you don't leave the window open to go there, you'll never find it. And you'll never see, like if you don't see what the tails are, you don't really know how the whole thing is shaped. And this just tells you a lot more about your problem. So if you were to look at just the points in isolation, it would be probably a fairly good description of how the banana shape looked. And maybe because of some symmetry, you would also be able to tell that even though this thing hasn't walked around enough to find this end of it, that if there is this tail, there might be that tail as well. So that's sort of a bit more nice visual intuition for what this looks like. And there are other algorithms on here that I haven't really looked at in the visualization before, but this is one that we're going to see in a minute that's really interesting. So one thing you might have noticed in the Metropolis Hastings section of this is you very often rejected proposals. I'd say red lines were coming up about 2-3 times as much as the green ones. And a red line is pretty much just wasted time. Like if I make a proposal and then reject it, then I haven't really learned that much more. I've just stayed where I am. I want a method that's going to let me make proposals and accept them almost all of the time. And this thing we're seeing on the screen is somehow magically doing that. The exact math of that, I honestly couldn't tell you off the top of my head, but essentially the idea we want to work with is it is making an analogy to a physical system. This is called Hamiltonian Monte Carlo. And if you've taken like the equivalents of like physics 105 or 137A or B, you might recognize that as just some math thing that describes a physical system. So we have a physical system underlying this, like a fake one, that matches the probability question we're interested in. And we time evolve along that. That's what these extra paths are. We like move that forward in time, we solve it, and we figure out where that's going to land. And where that lands is a proposal that has a really high probability of being accepted. And we're going to see that in action in our own code in a minute. So I think this is just a really cool way of working around a problem that you could just pick out visually. None of this really needs us to work directly with the probabilities. Well, deriving Hamiltonian Monte Carlo is, but understanding what it's doing on a qualitative level doesn't need us to get really in the weeds of like optimization math. And I think that's really cool. So let's start off with a quick refresher of what we did on homework 1. So this is the pi approximation analysis I was talking about. Of you make a bunch of points and you count them up. You count up how many are red in this case. And we did that. But we also did this. And we might have glossed over some of the code at the time. But essentially, this function right here that advances a state and accepts it or rejects it is a Metropolis Hastings step. So over here, I'm making a proposal by taking the spins we had and copying them and flipping a single site, and I get a new proposed state. If that proposed state reduces the energy, then I always accept it. If it increases the energy, I only sometimes accept it, according to this probability, which you might recognize as the Boltzmann distribution. And you ran that long enough, you ran that however many times we specified over here, just based on like tuning it and figuring out what worked. And you got a graph that looked something like this of the average spin. And this has given us a physical result that makes like intuitive sense of exactly as we expected. On the low end of temperatures, magnetism wins out. And then it gradually starts dropping until it's just about disordered at high temperatures. Interestingly, though, this is only the case, this sort of gradual drop is only the case for a one-dimensional system. This is one of the really interesting bits of like physical reasoning we can do. There is math that you can work out, and it's done over here in a lot more detail than I think we care to do here, but you can go to this link and it's really great exposition of this, that for more than 2 dimensions, for 2 dimensions or more, I should say, you get what's called a phase transition. I wonder if, sorry, I should have found this at some point before, but over here, they derive that there is a certain critical temperature that you can find through analytic calculations, after which you have a precipitous drop in this graph. You don't go gradually down, you go along, and then suddenly you drop all the way down. There is this fight, but instead of just being a gradual push and pull, thermal energy wins like all at once. That's really cool. I want to be able to find that with code. Here is code that does that. So this is something that I just got off someone's Stack Exchange post, but it's not that hard to, it's pretty similar to what I wrote for homework 1, just in 2 dimensions. And you could pretty easily scale this up to any arbitrary number of dimensions. Of course, there's not really much physical sense to more than 3 dimensions as far as I know, but it's cool to think about as a math concept. And there might be some ways that it does make physical sense. I'm no expert. So this is essentially doing the same thing of it checks if the energy goes down by doing the flip that we did. And if it does, then you make the flip. Otherwise, I'm going to generate a random number between 0 and 1. If that random number is less than this cutoff, the Boltzmann distribution cutoff, then I do the flip anyway. So that means I'm more willing to accept a small energy increase than a large one. And that kind of makes sense. I want to go like a little off a good point that I have. I don't want to go super far out. And so there's just some more code that helps over here. And over here, I've got this making a GIF of what happens to the spins over time. So yellow means spin up and black means spin down. Right now, I set the temperature to 0. Magnetism is winning over here. There is nothing happening. This is a GIF. This is showing the 20 frames that I had it plot, but nothing's really happening. Let's increase the temperature, see what happens. This is also like, there's some stuff about like what units were in here. I believe there is a T0, like a starting temperature that we're arbitrarily setting to 1 Kelvin. So really what we're plotting over here is T over T0, but we're just going to say T. Let's increase this to 1. Just-in-time compilation doing its job. It's like pretty easy doing all these flips. Making a GIF is a little more intensive, but here we go. You see, sometimes thermal energy wins out. As we go through this process, we're having it step through 20 times and flip every state if it's amenable to being flipped. Otherwise, keep it all still. And what we see over here is sometimes a spin down comes up. Sometimes it's like, yeah, this isn't exactly going to reduce the energy, but like the probability is high enough over here that it's willing to try like 1 at a time. But then it pretty quickly finds, yeah, no, that's not really going to help me, and it flips back. So you see these black squares popping up and then going away really fast. Let's increase this again. Okay, that reran, and now let's see what happens when this updates. Okay, That's a lot more interesting. This is all starting to be a bit qualitative in terms of how we're reasoning about it. But how I would interpret this qualitatively is while you have a lot more spin downs coming up because these are more thermodynamically favorable, this probability is even higher now when I reduce this, reduce the input to this by increasing t. It's still not staying where it is. I'm still just basically trying something, seeing it doesn't really work, and flipping it back when I have the chance. That's why you have like a lot more black spots show up, but none of them really staying in place. So I don't think we're at a phase transition yet. Let's increase it one more time. Now we're at something interesting. And yeah, I'm not sure. I'm definitely going way over time, and I don't want to try taking this out to more, and we can sort of see the behavior we want already, so I won't. Now we're seeing a black spot form, say, over here, and stay there for a while. At this point, it's pretty fair to say we may have crossed the phase transition boundary, because when you have a black spot, it's going to increase. It'll find out, hey, the sites around this might be favorable to being distorted as well. And it's really interesting to see it like stay. This is past the phase transition probably. The phase transition temperature we found back over here was 2.27, so 3 should definitely be past it. And this is what you would see over there. So there's some validation for what we're doing being generally correct. It's still just like an intelligent form of guess and check. And you can do this, like you can take this out to more data points and run these chains for longer than just these 20 points. And here's code that does that. And you find magnetization over temperature now shows a pretty sharp drop around this critical temperature that we were interested in, around 2.27. So it's pretty close to 1 all the way up here. And you can interpret magnetization as just very similar to average spin, or maybe exactly the same as average spin. And it drops really fast down to basically being disordered. Now thermal energy is the thing that's winning out. And it's really cool that we can just find that out by basically picking something, seeing if it wants to flip, and continuing to do that until we have enough for it to make sense. Okay, so that's one of the 2 examples of MCMC that I wanted to show off today in code. The other one is Hamiltonian Monte Carlo, which we already saw back in the interactive gallery over here. Like we said, this was a way of picking the proposal states such that we are more likely to accept these things. So over here, you see that borne out, at least in the first few steps, where the acceptance rate is really, really high. Acceptance rate of 1 means it's a better state, means you move there no matter what. But an acceptance rate close to 1 is interesting because it means you're not necessarily a better state. You're not a better state, because if you were a better state, you'd be moving there all the time, but it's close enough to 1. You've provided an almost equally good state that I still want to move to most of the time just to see what's there. So if you go back over to the HMC thing, you'll notice some of these paths that it's getting via the time evolution are really far. I'm not necessarily exploring like in my region like I was with Metropolis Hastings. Metropolis Hastings was just like, is making like pretty big circles sometimes, but circles nevertheless. If I'm here, I'm more likely to walk somewhere over here than over here. Not necessarily the case with Hamiltonian. Hamiltonian, I go wherever the physical system tells me to go. Like sometimes I go here, pretty close. Sometimes, yeah, that was a pretty far one. That was pretty close. Sometimes I'm going to make a really long trajectory just to end up back where I started. I'm sacrificing the idea of like locality in order to get these high quality proposals. And locality doesn't really help us anyway if we explore it well enough. And I'm going to show you in a minute what exploring well enough really means. So what I'm showing off today is also how this is really done in Julia in the Turing library, which has a bunch of cool MCMC techniques and a bunch of cool other inference techniques that you might want to use. It's a general purpose probabilistic programming framework that you should check out. It's turing.ml, I believe. Yeah, So you can read more about this here. The documentation is quite good, and it's one of the more well-supported and well-known Julia packages, as far as I know. So that's definitely worth checking out. And one of the things they pride themselves on is robust, efficient Hamiltonian Monte Carlo sampling. So let's see what that's about. So to start off here, I've made a model of how things work in this made-up probability world that I'm constructing. And you don't have to understand what exponential and normal are, but the important things to take away here are I'm going to observe some variables x and y. And they're going to depend on some hidden variables s, m, and p. I set s according to some fixed distribution, m according to s, p also according to s, then x according to m, and y according to p. This is pretty similar to, but not exactly the same as the example they had in their documentation. I altered it to have 3 variables because I want to show some stuff off with 3 variables. So this is defining a 3-dimensional space, very similar to the MB plots that I showed back when we were talking about what MCMC is as a concept. And essentially what I'm doing each time is I'm picking a new value of S, M, and P that's also fairly likely to be accepted. There's a lot of like physics reasoning here. You see there's an energy and an energy error as to how this is made, but let's just be satisfied that they make these choices. And you sample, you take 100 samples just to start with, just to get an idea of it from here, and you get some estimates of these things. M is this thing with this standard deviation, and there's some other like ways of measuring the error on these and some confidence intervals. P is this with this standard deviation, S is that with that standard deviation. And you can also plot these. You can say, this is where the chain went over time. If I just look at M, it started pretty close to 0, it looks like, went down a bit, up a bit, down a bit, and just like over time found the better places to be. And you got this sort of like histogram or density plot. This is what P did. And P has a sort of strange bimodal thing going on, and we'll discuss that in a minute. And this is what S does. So you've got these plots, great. And then what's really common with MCMC in general is working with what's called a corner plot. This is a corner plot that I just made. There are ways to do this like canonically in Julia, and there's the corner package in Python. And also there's the MC package, which is like MC corner in Python. Whereas in Julia, I would use like plots for the plots and Turing or something similar for the MCMC. But a corner plot looks like this. On the diagonal, I've got these density plots or histograms of what these variables are doing. I want them to look roughly like this one does, but probably a bit more well-defined. Like you see over here, I've got this extra thing tail, and maybe it's, excuse me, maybe that's a part of how the data actually are. Maybe that's an artifact of not running it long enough. How you can tell which one it is by the off-diagonal ones on the bottom left. These are scatter plots between each variable and each other variable. They're exactly like the parameter space plots that I drew out by hand, and they're just all the points you visited. Sometimes you will throw out, say, the initial, like, maybe even 1,000 steps, but the initial, like, 10% of what you do, because you're still getting to the regions of high probability. I haven't done that here, but you might want to do it when you're getting real science results out of this, and that's called a burn-in. Anyway, I haven't burned in here, but you should if you're doing it for anything serious. And in fact, in homework 1, I did have you use a burn-in and throw out the first 1,000 samples. So over here, looking at these, there's a lot of scatter to it, and that's like not ideal. In general, like I showed you when I was drawing it out, I want these to be pretty tight circles. I want there to be a clear central point in MS space, in MP space, and in SP space. Labels got a little strange on this. Yeah. Yeah. Oh, sorry about that. This one should be SP. If you notice here, this one's S vowels, this one's P vowels. Yeah. And in SP space, I want there to be a clear center and a clear amount of spread, and then I can be sure it's converged. So I did think this is converged because I only did 100 steps, and that's not really a lot. Like if you have 2 to the 100 spins, for example, not this is an Ising model setup, but if by analogy, if I had 100 spins and I only had 100 chances to flip it, I wouldn't get close to exploring all of the like 10 to the 30 possibilities. So let's increase it to a more reasonable number. Let's go 10,000. And this is going to take a few seconds. And over here, I think there was actually a loading bar or something. Oh, no, it's saying, no, it's just refreshing all of these things. Yeah. And now I've got a much more dense plot of where I've walked in M, P, and S, and I've got much more well-defined graphs of where these are and how certain I am about them. You'll see that the little hump over here in P is gone. Just that was an artifact of not really looking around enough. I looked around enough and I'm there. And now these corner plots look quite a bit nicer. And there's ways to make these a little more like aesthetic. These are just like bare bones ones to get the sense across that I plotted. But I see a lot more clustering now. I can pick out a center of this. I can pick out a center of this. I know about how certain I am. And these all look about like a normal distribution, about a bell curve. This one's not a bell curve, but only because I've restricted it to be positive. This one looks like an exponential curve, which is exactly what I actually set it to be. So this is a lot more encouraging in terms of being a good MCMC result. This is what you should be striving for in your own science. Okay. One more thing that might be fun to look at is the acceptance probability over time. Like I said, with Hamiltonian Monte Carlo, it's essentially the same as Metropolis Hastings, except I am choosing things such that they have a really high probability of being accepted. And in fact, here you'll see at no point did the chain ever pick a proposed state that had a less than about 85% chance of being accepted. This is the lowest one. Most of them are above 90, above 95 even. Like a lot of the time I'm picking states that are strictly better. And even when I'm picking ones that are worse, they're still like close enough to good that I want to explore them. And so I've done this and I've gotten a really good sense of what my space looks like and been very efficient doing it. So I just think that's really cool. Okay. So hopefully I have given you some insight into what these tools are, why we use them, what to look out for when you are using them, even if you don't know all the math details yet, or you don't want to learn all the math details yet. And this is a window into a whole range of interesting science you can do. There's a lot working with like large data sets that you just can't get across with simple models that you really need to explore in this way and just walk around and see what happens. And this is a really great starting point, I hope, for you to be able to do that for your own science. Thanks very much for watching.